Today we're going to start a new unit on electromagnetic radiation. 2 units ago we did electricity. Last unit we did magnetism, and certainly there was some interaction between the two, electricity and magnetism. One can cause the other can cause the first. There was some relationships between the two, electricity and magnetism. Today we're going to take that a step further. It's going to be a little bit different than our last 2 units. We're not talking about electric fields so much, and magnetic fields, at least after we get the introduction out of the way, at least. We're going to look at more the effects and what electromagnetic radiation does. So what is electromagnetic radiation? What is it fundamentally? Well, it is energy. That's what it is. It's energy. It's pure energy that travels in a wave-like form, just like water waves travel in a wave-like form, except that electromagnetic radiation doesn't require a medium. It can travel through empty space, and it does all the time, right? Light comes from the sun to the earth in about 8 minutes. It travels mostly through empty space. Now, it does travel through air as well. You don't need empty space, but at least with a mechanical wave like sound or like water waves, you need a medium. Okay, with electromagnetic radiation, okay, it's energy that travels in a wave-like form without the need for a medium, without the need for a material to travel through. So what does it look like? Well, it doesn't matter what kind of EMR we have. When I say EMR, by the way, that's just an abbreviation for electromagnetic radiation. It doesn't matter what kind of EMR we have, whether it's the radio waves or the microwaves or the infrared or the visible light, or what were the other kinds you saw in the video? Ultraviolet, X-rays, gamma rays. Doesn't matter what kind you have, they all consist of the same thing. They all consist of 2 waves. 2 field waves, an electric field wave and a magnetic field wave. We've got 3 axes, X, Y, and Z. Hopefully I can draw this so that it kind of makes some sense here. If we have an electric field wave that's on the positive Y-axis, or at least a part of an electric field wave that's on the positive Y-axis, then we may very well have a magnetic field wave that's on the positive Z-axis. Okay, does that diagram make sense there? We get 2 crests, an electric field crest on the Y-axis, a magnetic field crest that I'm trying to draw kind of in 3 dimensions there on the Z-axis. Well, a changing electric field will produce a changing magnetic field. So the blue one produces the red one. And a changing magnetic field can produce a changing electric field. Now, a changing electric field can produce a changing, it's getting hard to draw now. A changing magnetic field, which is my red one there, can produce a changing electric field. And a changing electric field can produce a changing magnetic field, and so on and so on and so on. So that in the end, what you end up with here is a wave that moves from the place that it was produced to some other place. Take a look up here for a second and watch my hands. This is really hard to do. If you don't believe me, try it. It's kind of like the rub your head and pat your belly or whatever it is. It's hard to do both of them at the same time. Watch my one finger here, my left finger, which is going to be my electric field, my vertical axis on the Y-axis. Okay, my right finger is going to be my magnetic field on the Z-axis. Okay, so the wave looks like this. Okay, you've got an electric field and you've got a magnetic field. Okay, the electric field that was this crest produces a magnetic field that is the trough of the magnetic field. Does that make sense? So it looks like this. Okay, so you've got electric field and magnetic field, electric field and magnetic field troughs, electric field and magnetic field crests, electric field and magnetic field troughs. Can you see what I'm trying to do there? Okay. One makes the other. Electric field doesn't make electric field makes magnetic field, and magnetic field makes electric field. So that's why when it's produced over here, you don't just have this, okay? This makes this, and then this makes that, and so on and so on and so on. That's how it moves from the place it was produced to some other place. That's why when you flip on the light switch, the light actually travels from there, from the light, to you. Because the crest of a magnetic field will make an electric field, and an electric field will make a magnetic field, and so on and so on and so on. Make sense? Kind of? So this wasn't new. Part of it was, but the beginning wasn't new. Maxwell knew very well that a changing magnetic field would produce a changing electric field. Okay, that was well established. He didn't discover that. But he did hypothesize that by symmetry, a changing electric field might make a changing magnetic field. So now if you have a changing magnetic field producing an electric field, and an electric field can produce a magnetic field, then it just becomes a circular thing, a self-sustaining thing. Now, it doesn't mean that you're creating energy. We started off with this, right? Well, if we have 1 second later, this, and then a second later we have this and this and this, then we've just got 3 parts when we only had 1 part. We've created energy. Well, it doesn't quite work that way. Part number 1 produces part number 2. Part number 1 disappears. Part number 2 produces part number 3. Part number 2 disappears. Part number 3 produces part number 4. Part number 3 disappears. Unless the source of that EMR is still there. Unless the source of it, whatever's causing it, is still there causing it. What causes it? On the next slide, I guess it says it on this slide as well, accelerating charges. Accelerating charged particles. Charged particles at rest produce a gravitational field, an electric field, that's it. Charged particles that are moving at a constant speed produce all 3 fields, electric, gravitational, and magnetic, but they're constant fields. Charged particles that are accelerating produce changing electric and magnetic fields. Okay, that's what we need here, is accelerating charged particles. If we have a charged particle that's accelerating and constantly accelerating, back and forth, back and forth, back and forth, then as number 1 gets replaced by number 2, then you get a new number 1. And as number 2 gets replaced by number 3, then you get a new number 2, and so on and so on. Make sense? So if you just have a quick acceleration of a particle, you get a pulse of a wave. Okay? Number 1 gives way to number 2 gives way to number 3. But if you have a still accelerating charge, it's still accelerating, the source of the field is still there, then you're going to get number 1 replaced by number 2, but number 1 is going to form again as a result of that accelerating charge. So you end up with this, basically. An electric field and a magnetic field, 2 sine waves in phase with each other. That means crest and crest are together, trough and trough are together. 2 waves, electric field wave, magnetic field wave, in phase with each other, both perpendicular to each other, and both traveling perpendicular to the fields. Somebody in my period 1 class, as we were going over the test on Thursday before the break, I forget which question it was they were talking about now, but basically he said, I picked C because it said perpendicular. And everything in magnetism is always perpendicular. Like, oh, that's pretty good reasoning, actually, because things in magnetism are almost always perpendicular, right? Okay, no change here. Okay, magnetism is involved here. The electric field is perpendicular to the magnetic field. Both of those fields are perpendicular to the way the wave moves. So if you got a field on the x-axis, on the y-axis, you got one on the z-axis, it's going to move on the x-axis. If one's on the x and z, it's going to move on the y-axis. If one's on the z and y, it's going to move on the x-axis. Okay, you got 3 axes, all 3 of them are going to be involved. One field on one axis, one field on another, and then it's going to move along that 3rd axis. What's the cause of this again? We know what it looks like. Okay, we know what the field looks like. Okay, what EMR consists of. What causes it? Yeah, not a charged particle. Okay, not a moving charged particle, an accelerating charged particle. Now, all of those 7 types of EMR that you saw in the video are a little bit different, but they're all caused by different mechanisms, but in general, it's all accelerating charges. It's just the exact mechanism that varies, and we'll talk about that a little bit later on. This little applet now shows us the same thing, but this one's animated, so it's the process of an electric field wave changing in value, a magnetic field wave changing in value, the electric field causing the magnetic field causing the electric field. So we have one field here, the red field, that they're calling the electric field on the y-axis. Okay, the blue field on the z-axis. Doesn't matter which is which, really. They call the red one the electric field, the blue one the magnetic field. Doesn't matter which one's on the y-axis, which one's on the x-axis, as long as they're perpendicular to each other. Which way is it traveling? Which way is the wave moving? You can see the energy is going on the x-axis, right? All 3 axes involved here. Okay. Make sense? And you can see here, even still here, you can see that we don't have the field itself moving. We have the energy being transmitted via the field changing in value. So we have a field line right here. It's getting smaller and smaller and smaller and bigger and bigger and bigger. Let's take a look at this one here. It's getting bigger and bigger and bigger and bigger and bigger. So the field is changing. Now it's getting smaller and smaller and smaller and smaller. And pretty soon it's going to start going down like this. All right, we have a changing electric field there, okay, that in the end is producing a changing magnetic field line and transmitting the energy via that changing electric and magnetic field. Does that make some sense? Kind of? All right. Now, we've talked about this electromagnetic radiation as being a wave. In fact, 2 waves, the electric field wave and the magnetic field wave. There is evidence to support the wave nature of this. In other words, there is evidence to support Maxwell's theory of electromagnetic radiation that it consists of waves. There's four things here, 4 properties of waves that electromagnetic radiation exhibits. Polarization, you don't really know what that is yet. We'll talk about it in a second here. Diffraction, you learned about that in physics 20. You got an opening, and a wave goes through that opening, and what happens to it? It spreads out, right? It spreads out. It diffracts. That's a property of a wave. When a water wave goes through an opening, it will spread out. It will diffract. Since electromagnetic radiation will also diffract, and we know that because we've seen it diffract, then that's evidence to support the wave nature of it. Okay, if it exhibits a wave property, then it must be a wave. Interference. Well, interference is when you have a crest and a crest meet each other, you get a bigger crest, constructive interference. Or a crest and a trough meet each other, you get nothing. They cancel out, destructive interference. That's a property of a wave. So electromagnetic radiation, if it exhibits interference, if you get brighter light when a crest and a crest meet each other, then it must be a wave. It supports the wave theory of light, the wave theory of EMR. Refraction is the bending of a wave. When water, for instance, goes from one depth to another depth at an angle, its direction will change. The water wave's direction will change. And you guys have seen that sometimes on a beach. Okay? If you see a water wave coming in at an angle and it strikes and it hits all of a sudden a different depth of water, there's a big drop off in the depth of water, then the direction of the wave will change. It will bend as it's coming in towards the shore. That's called refraction. It's a property of waves. If EMR undergoes refraction or bends, then it must be a wave. If it exhibits a wave property, it must be a wave. Finally, polarization. That's the one that you've probably heard of before, but don't really know what it is, because we haven't talked about that in physics 20. Polarization is also a property of a wave. Let me give you a little analogy here for a second here. We've got a piece of plywood. And in that piece of plywood is, let's make it a smaller opening, a hole that's cut in it. This narrow vertical hole in it. We got a rope, and that rope goes right through that hole. We can fling that rope like up and down or sideways and produce waves in that rope, right? Diagonally produce waves in that rope. If we make a vertical wave, then that wave will transmit through that hole. If we make a horizontal wave in that rope, what's going to happen? It's going to get stopped by that piece of plywood, right? The horizontal wave can't go through there. If we make a diagonal wave, it's going to get stopped. In other words, it's vertically polarized. It's only going to allow a certain component of a wave through the hole. It's vertically polarized. Well, if light can be polarized, in other words, if we can filter out all but one component of light, sometimes you have part of the light like this, and sometimes it's like this, right? Two waves, right? Both perpendicular to each other, but in all different orientations like this. If we can filter out all but this, or all but this, or all but this, then we can polarize that light. And if we can polarize it, then it must be a wave, because that's a property of waves. Make sense? Okay, you see the demonstration that we just did here, guys? Okay, we filter out everything but the vertical. Okay, that's great. We filter out everything but the horizontal. That's great. If we put them both together, then we filter out everything but the vertical here, everything but the horizontal here. Put them both together, it's everything literally, including the horizontal and the vertical filtered out. That happens with light. You just saw it in the demonstration. Okay, light polarizes. Therefore, since light polarization is a property of waves, and light exhibits, or electromagnetic radiation exhibits wave properties, then it must be a wave. Caden, question?
When you rotated them, that just means that the horizontal
Yeah, no, that's exactly it. When I rotated it, okay, right now, if these two polarizing filters are one in front of another right now, you're going to filter out everything, right? But if we rotate this one 90 degrees, then what's going to happen? We're going to have two of them that are polarized vertically, which is going to allow the vertical component still to go through. That make sense? Do a couple quick multiple choice questions. Don't worry about taking out your phones and submitting these ones, okay? We'll just do these ones as a group here. 97 says electromagnetic radiation, or EMR, is produced by charged particles that are moving what? Well, they give me a bit of a break here, actually. I wouldn't have even told you this. That's where I would have stopped. If I made up this question, I would have said electromagnetic radiation is produced by charged particles that are blank. At rest? No, not at rest. Charged particles at rest produce a gravitational field and an electric field, but that electric field is not changing. We get charged particles that are moving here. What do they produce? Well, charged particles that are moving will produce a gravitational field, an electric field, and a magnetic field. But what condition has to be met in order for electromagnetic radiation to be produced here? In other words, in order for an electric field and a magnetic field to be produced that's changing. Well, traveling at the speed of light? No. Electromagnetic radiation travels at the speed of light because it is light. But the particle that causes it isn't traveling at the speed of light. What about with zero acceleration? What does that mean? Yeah, it's either stopped or it's traveling at a constant speed. If it's stopped, it'll produce an electric field and a gravitational field, no magnetic field. If it's moving at a constant velocity, it'll produce all three of them, but the electric field and the magnetic field won't be changing. So that doesn't work for us either. With a changing velocity, that's an accelerating charge, right? That produces a changing electric field and a changing magnetic field. That's EMR. So this one seems to work. Parallel, you can almost throw that one out because you see the word parallel, right? Parallel to a fixed magnetic field? No. C is the answer. 105. Maxwell's work contained the new idea that what? An electric current in a wire produces a magnetic field that circles the wire. That sounds familiar. That must be right because it sounds familiar. No, it's not. I see a few people shaking their heads. No, it's not right. How could we change this question to make A the correct answer? It's not right now. What could we change in the question that would make A the correct answer? Yep. No. No. Get rid of one word, but not that one. Change Maxwell to Oersted. Oersted's work contained the new idea that an electric current in a wire produces a magnetic field that circles the wire, right? So A is not the right answer for Maxwell. It is for Oersted, but not for Maxwell. B, a current is induced in a conductor that moves across a magnetic field. That's also not the correct answer. But we could quite easily change the question to make it the correct answer. What would we have to change it to? Not Maxwell, but, oh, you guys. No, that was Oersted. Faraday? Yeah, Faraday. Faraday. So B would be correct if it was Faraday, not Maxwell, but it doesn't work for Maxwell. C, an electric current that changes with time generates a magnetic field. That sound right? C works. What is electromagnetic radiation? What's it caused by? A changing electric field makes a changing magnetic field. A changing magnetic field makes a changing electric field, and so on. C works. Two parallel current carrying wires exert a force on each other. They do, but it has nothing to do with electromagnetic radiation. So the answer for that one is C as well. Okay, good news. This is the last slide that I want to put up today. And it's only 1:37. We're going to say quite a few things about this slide, but still not going to take us the next 30 minutes. The 7 types of EMR that you saw in the video, that you heard in the song: radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. You can remember them from the song, and you will. Trust me, you will. Okay, you're going to get that song stuck in your head. How many people have it stuck in their head right now? Okay, I have a solution, by the way, to that. There is only one solution to getting that song out of your head. I want you to, for 1 second, Caden, just to stop. Carefully think about what a fox says.
No.
Now the electromagnetic radiation song's out of your head, right?
I've never heard the fox.
All right. So we have 7 types. We can remember it by the song in the order, and that's correct. It works great. But we can also look at this. Visible light consists of Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. The word infra means below. So below red would be infrared. The word ultra means above. So above violet would be ultraviolet. And then it means filling in a couple: X-rays, gamma rays, microwaves, radio waves, and so on. But that gives us at least a core to start off with. Now, how are we ranking these? We start off with radio waves and end off with gamma rays in terms of frequency. Radio waves have the lowest frequency. Gamma rays have the highest frequency. Frequency is how many waves per second that we have. So a radio wave that has a low frequency will have the waves spread apart, not many waves per second. Whereas a gamma ray that has a higher frequency will have the waves kind of scrunched together, right? More waves per second. If you have a low frequency, then the wavelength, the distance between crest and crest, will be high. So a low frequency corresponds to a high wavelength, and a high frequency corresponds to the low wavelength. Now the energy, you're going to have to just trust me on this one for now until later on in the unit. A low frequency also corresponds to a low energy, and a high frequency corresponds to a high energy. You'll see why that's the case later on in this unit, but for now, just trust me on it. All right, we have to look at 2 aspects of each of these types of EMR here. The first one is, what causes it? Well, in general, we know it's accelerating charged particles. Accelerating charged particles produce all of these types of EMR, but specifically, there are mechanisms by which each of these are produced. We're going to group them like this. Radio waves and microwaves are produced more or less by the same mechanism. That's an oscillating electric charge. What do we mean by an oscillating electric charge? Back and forth. an electric charge going back and forth, like an electric current going back and forth, an alternating current, an AC current that exists in your houses. How many of you guys have ever noticed this? You're driving down the highway listening to the radio, you go onto a power line, and all of a sudden your radio cuts out for where you get kind of fuzzy radio reception. You ever notice that? It's because the oscillating electric current through that power line is generating radio waves. And those radio waves that it's generating are interfering with the radio waves that you're trying to listen to until you get past it. And then it goes back to normal because there's no longer any interference. The oscillating electric charge produces radio waves. The next three, infrared, visible light, and ultraviolet. Infrared, which by the way is heat, right? Thermal energy, heat. They're all produced by the same basic mechanism as well, and that's transitions of electrons. In atoms. Chemistry people, maybe some of you guys have learned about this a little bit already, have you? If the electron it can jump to a higher level, it can fall from a high level to a low level. When it does that, when it falls from level 5 to level 2, it gives off electromagnetic radiation. Okay, each different transition will produce a different frequency of EMR, corresponding to either infrared, visible light, or ultraviolet, or occasionally X-rays, but not usually. Usually it's just infrared, visible light, or ultraviolet. Transitions of electrons, E negative. Yeah, in atoms. X-rays. How many of you guys have ever gone to the dentist office, got an X-ray, and been comfortable as you're sitting there, kind of lying there, as the dental hygienist is saying, talking to you and making small talk, whatever, and she puts that thing in your mouth, and then she puts that X-ray machine next to your mouth. Okay, you're all okay until she says, "You ready?" And you say, "Yeah," and then she runs away and presses the button. Yeah, she puts the lead blanket over you first, yeah, to protect important parts of you, and except your brain, yeah. And then she runs away. It's like, wait a second. If this is safe for me, why isn't it safe for you? Well, it's safe for me because I have one of them a day, once a year. She has 50 of them a day, right? Every day of the year. She has to run away and hide because that electromagnetic radiation, it's ionizing radiation, and it can cause damage. It does cause damage. Once, your body repairs itself quite efficiently. But 50 a day, your body can't repair itself that quickly. That's why she runs away. In the end, how are these X-rays produced at the dentist office or in any other place? Well, in theory, it's quite simple. You accelerate electrons to an incredibly high speed, to a very, very high amount of kinetic energy. And then we smash them into a metal target. We stop them. They decelerate quickly. They rapidly decelerate. The kinetic energy that the electrons had as they were moving at an incredibly high speed has to be converted to something that gets converted to X-rays. Well, gamma rays can be used in some cases for diagnostic things like CAT scans or whatever, but not necessarily. Gamma rays have more ability to penetrate matter, and we'll talk about that more as time goes on as well. So generally they're used for talk about medicine as much for treatment as they would be for diagnostic, whereas X-rays would be limited pretty much to a diagnostic thing. Gamma rays are produced by nuclear decay. And what do we mean by nuclear decay? In chemistry, you learn about things that happen to the electrons, sharing electrons and trading electrons and chemical reactions involving electrons and so on. In nuclear physics, we talk about what happens to the nucleus when a nucleus splits up, when it changes into something else. Okay, that's nuclear decay. When matter is converted to energy. That might sound a little bit weird. Somebody this morning asked the question, well, didn't we learn back in grade 9 that matter can't be created or destroyed? That's a bit of a lie. Didn't we learn in Physics 20 and Science 10 that energy can't be created or destroyed? That's a bit of a lie. What we really mean is that matter and energy combined can't be created or destroyed. You always have the same total amount of matter/energy in the universe. But matter can be changed into energy, and energy can be changed into matter. So really what we should say is we have the law of conservation of matter/energy, not two separate laws. It's really the same thing. We'll talk more about all of these types as time goes on. Now, do you want the good news or the bad news to finish things off for today? Want the bad news first? All right. Bad news is this. There are 7 types of EMR. Each of them have a range of frequencies, wavelengths, and energies. You need to be able to determine what type of EMR you have based on any frequency, wavelength, or energy. In other words, there's 21 different ranges that you have to know. That's the bad news. Now, do you want the good news? Be glad you have me as a teacher now as opposed to, say, 15 years ago. Because 15 years ago, this thought never occurred to me. I don't know why it didn't. But I don't know when it was that this occurred to me that, wait a second, we don't have to remember 21 different ranges. We have to know 21 different ranges. We have to remember 3. We have to remember, this is at least the way that I would do it, we have to remember that infrared frequency is 10 to the 9 to 10 to the 12 hertz. Sorry, microwaves, I should say. Wrong one. Sorry if you drew it, all right, I'm sorry. 10 to the 9 to 10 to the 12 hertz. If you're too mad at me for making that mistake, then I'm not even going to tell you what the shortcut is. Remember all 21 of them. There. 10 to the 9 to 10 to the 12 hertz. Remember that visible light, got to be a little bit more specific on this one, it's 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz. I don't like remembering those numbers any more than you do, but we have to. X-rays are 10 to the 17 to 10 to the 20 hertz. The good news is that's all we got to remember. If you're given a frequency of EMR that's 10 to the 6, what is it? Wait a second, I didn't remember that one. What am I supposed to do? Well, it's not radio waves, so it's got to be, sorry, it's not microwaves, so it's got to be radio waves, right? If I have one that's 10 to the 13 hertz, well, it's not microwaves and it's not visible light, so what is it? It's got to be infrared. Visible light is 4 times 10 to the 14. Here, let me write that again. To 7.5 times 10 to the 14 hertz. So if it falls in one of those 3 ranges that you've remembered, then great. If it doesn't, then figure it out. Now, what if you're given a wavelength? What if you're told, hey, look, the wavelength of this EMR is 6.0 times 10 to the -7 meters. Does that mean we have to remember 3 different wavelengths as well? No. Figure out the frequency. From physics 20, you remember that V is equal to F times lambda. Frequency is therefore V over lambda. The speed of EMR, no matter what kind you have, visible light or any other kind, is 3 times 10 to the 8. Divided by 6 times 10 to the -7, that gives me 5.0 times 10 to the 14 hertz. What kind of EMR do we have? Visible light. So now we've remembered 3 different ranges of frequencies, but given any frequency or any wavelength, we can determine what kind of EMR it is. We can do something real similar with energy. I'm just not going to show you what that is yet because the equation that we have to use, we haven't learned yet. Okay, we'll learn that later on in this unit. Okay, just trust me now that you can figure out, you will be able to figure out what the frequency is from the energy. It's not hard. It's just a new equation that I don't want to go through right now.